Welcome back to this plenary session in GRA 6036. We are doing project 13 and we'll now do the last exercise, exercise H. But before we do that, just one comment about the plot we made in here. So we had, we had this plot. Well, maybe I added some xlab and ylab and main to make it nicer. And we were also supposed to add a legend. So a legend is something, a little box explaining what these two lines correspond to. So I did that after some, well, I needed to Google it to remind myself what's the syntax for adding a legend. But here it is. So you write legend, and you here indicate where on the x-axis you want your legend, where on the y-axis, then what it is supposed to say. The color of the lines, and here we say there are to be lines, and this bty equals n means remove the box. So okay, I'll show you. So first, let's run this. You get this thing. So these are the two lines, and the colors we specified for two lines are here, red, blue, and these. So the ordering here is important. So quadratic model corresponds to red, cubic to blue. Okay. And then I like adding bty equals n because then you remove, well, you see, you remove this box around it. Okay, so if you had one more line, let's say you had a line 3 that was green, you could write line 3, and then you must add green, and then you get a green line. Like this, but there is no green line, so let's take that away. So legends are nice to add to plots so that the plots are easy to read. So now let's do exercise H. So in this exercise so you should read this stuff and try to understand why we are doing this. But in this exercise we are going to test this complicated model with interaction terms against this simpler model. An important thing to notice in this model is that this cubic term is only present for the good-looking group. Notice that here, x pure and x pure squared is for both groups, while this beta 4 x pure and beta 5 x pure squared is only for the good-looking group. So when this takes the value, the GL takes the value 1. And I see another typo. It's supposed to be an I here and an I here. So I'll fix that. But anyways, so with these terms, I mean, they both have an effect of x pure and an effect of x pure squared. That's for both groups, but the effects are allowed to differ between the two groups, while the cubic term here will only be present for the good-looking group. So the cubic term is playing a somewhat different role than these two terms. Okay, so let's fit this model and compare them via an F test to test the hypothesis. So now we want to test the hypothesis that beta 4 equals 0 and beta 5 equals 0 and beta 6 equals 0. So that's 4, 5, and 6. So then let's call that fit 4. I don't know if maybe I've used that already, but now we're supposed to fit it on the whole data set. So that's log wage, bty, gl, plus bty, x pure, plus I, x pure squared, and then the interaction terms. So multiply this by bty gl, $sign gl, and multiply this thing by bty gl plus bty power 3 times gl. And now it says in the exercise that R will add this term by default if we do not subtract it in the model. So let's just we'll believe that that is true and we'll subtract it. So the point is that since what this is saying is that it's so common when you have an interaction term, for example, between x squared squared and GL, that you also have this x squared term separately. So if you do not include this text says that, well, then the LM function will just add it and suppose that you just forgot about this term. So then we have to say explicitly to R that, well, we do not want this term by subtracting it. That's the syntax for it. Okay, so let's fit this model and do summary. Well, so here it is. So now we're looking at this individual test, but we want to do an F-test to compare this model to a simpler model. So I guess we already fitted that model, but let's just do it one more time. So this is fit age is then the simpler model, which is let's see, is it this model? No, it's not this model. We want the same intercept for both groups, so we have to remove this GL thing. So we fit that model, and now we can compare these two. Models by an F-test. So now we're testing this hypothesis. So that's fit age, fit 4. We run this test. And well, so fit 4, fit 4. So it should possibly fit age. That's why we got this. And now I forgot to comment this out, so we'll do it one more time. Okay, so fit this model with summary, fit this model, and now we do the F-test. Here we go. Okay, so well, now we see that this this is the p-value, and this is significant at the 5% level, and well, I mean, it's even significant at the 1% level. So the conclusion of this F-test is that, well, the more complicated model is a better model than the simpler one. And this we should then compare with, I mean, we can just do it right here. So interesting thing then is to, if we do fit 4 simple, I think we fit this model above, where we remove the quadratic term. So now we want to assess if this model that does not include remove the cubic term, where we do not include the cubic term, is better than this simpler model. So let's do that. So now we're testing against fit age. So now we're testing this hypothesis again. We did that above, but let's just compare it. So this is fit 4 simple. Okay, and this is what we did above. Notice here it was not a significant. This is not significant. So the conclusion from this test is that, well, the simple model is better. But when we added this cubic term, we got the conclusion that here we rejected the null hypothesis of the simple model being best when it competed against the model with the cubic term. But when we competed against the model that did not include a cubic term, we did not reject the null hypothesis. Okay, so that was it for today.